Hey everybody, if you remember back to our discussion of orbitals and electron configurations and that sort of thing, these are those S, P, D, and F types of orbitals. It turns out that when we bond, we don't use those quite as easily as you might think. So we talk about something called hybridization in this video. So we know about Vesper theory. We know that we can use it to predict shapes. Why can we do that? Because valence electrons repel one another. But it turns out that that doesn't tell us very much about how the orbitals actually rearrange with themselves to make this bonding happen. And a good way of us thinking about hybridization is that it is basically mixing two different orbitals, and that produces new orbitals that are a little bit easier to bond together. So for instance, if you had some strawberries and you had an orange and you wanted to blend them together, some ice, you'd make this delicious smoothie, right? It's not really a strawberry, it's not really an orange, but it's a combination of the two of them that's a little bit better than either one by themselves, right? It's this delicious final product. And so we can do the same thing with orbitals. Now, you can go very much in depth with hybridization of orbitals. We can go on to college level, AP level sort of things. We're going to get a very cursory overview today. And then you can take this further in your chemistry career if you so desire. But for us, simply, it turns out that we're only going to hybridize S and P orbitals. Now you have this table. Stay here for a second. Let me show you what these might look like. Right, so we've talked about S orbitals looking like a sphere, P orbitals looking a lot like this SP orbital you see on the side. And if you put those together, if you kind of embed this sphere in here, imagine that there's like a little sphere sitting down there, and that would be a combination of an S and a P orbital. And it turns out if you put them together to make this, you get an sp2 orbital, and this is an sp3 orbital. So we're going to put these together much like the strawberry and the orange to make new orbitals that are combinations of the original orbitals that we were dealing with. So that is very much dependent on what your atom looks like in your Lewis structure. So what I mean by that is if you look at your central atom is going to have a certain number of electrons around it. Those electrons can exist in either lone pairs or in bonds. And the type of central atom that you have and how many bonding and lone pair locations it has is going to dictate what type of orbital is formed. So first off, if you put together an S and a P orbital, that is a grand total of two orbitals, right? 1s, 1p, you're going to make sp. If you put together an S and P, 2p orbitals, we call that sp2. And we'll actually rewrite this as a superscript. Let's write this as sp superscript 2, but it's a grand total of three orbitals. And if you put together four orbitals, an S and three p's, remember, valence electrons, 8 total valence electrons. If you had one S and three P orbitals, each one can hold 2 electrons, so there are your 8 valence electrons in your octet. You have this full octet. This is going to be an sp3, 3 is a superscript, hybridized orbital that comes together to allow you to bond. So if we asked you, what sort of orbital are these electrons sitting in when they bond, the answer is no longer just an s orbital or a p orbital. It's one of these hybridized orbital, either sp, sp2, or sp3. Now, how can you figure that out? Well, here are the geometries associated with each type. So remember, linear is AB2. I'm going to write out the Vesper model for each of these. Trigonal planar is AB3. The bent with one lone pair is AB2E. We know that tetrahedral is AB4. Trigonal pyramidal is AB3E. And bent with two lone pairs is AB2E2. So let me do something. Let me add together in each one of those the total number of things around the central atom. The things could be one bond, one lone pair, or any combination of that. So this one has 2 bonds. It has a grand total of 2 things around it. This one has 3 bonds, 3 things around it. 2 bonds plus 1 lone pair, 3 regions of electrons around it. 4 bonds, 4 regions of electrons around the central atom. 3 bonds, 1 lone pair, 4 regions of electron density around the central atom. 2 bonds, 2 lone pairs, 4 regions of electron density. So what you'll start to notice is that the hybridization that accounts for 2 orbitals is the one that has 2 things around the central atom. So anytime you encounter something with 2 things around the central atom, things being either bonds or lone pairs, we're going to say that the bonding exists in sp hybridized orbitals. And these are the names, these are the shapes where that occurs. Anytime you have 3 things around the central atom, either 3 bonds or 2 bonds, 1 lone pair, 3 total things, you need 3 total orbitals, you'll be sp2. So trigonal planar and bent with 1 lone pair are always sp2 hybridized. Anytime you have 4 things around the central atom, you need 4 orbitals to store them, you're sp3 hybridized. So tetrahedral, trigonal pyramidal, or bent with 2 lone pairs, those all have sp3 hybridizations. And that's where we'll stop with our study of hybridization. You can go crazy into DNF orbitals here, but for our purposes, this is good enough to recognize what type of hybridization is required for every type of structure that we build based on its Vesper model and therefore its shape. Now, another thing that we should discuss as we're thinking of hybridization is the polarity of molecules. So we know all about polar bonds, right? We said that you have electronegativity differences of 0 to 0.3, and that's nonpolar. And 0.3 to 1.7, or excuse me, 0.4 to 1.7 is polar, and above that is ionic, etc. Right? And so what that does is it allows the more electronegative atom to pull electron density towards it, and that makes regions of partially positive and partially negative charge. And so if I drew water in here, water is H2O. Oxygen is way more electronegative. And just so you know, the Lewis structure actually looks like this. There are 2 lone pairs like that. So oxygen is really electronegative, so that means it is partially negative, whereas hydrogen becomes a little bit partially positive. This little part of a figure 8 is a partial symbol. Now, this is not enough to be ionic. We're not transferring electrons, but it's enough of a difference in electronegativity in order to indicate that there is a separation of charge there. And so we can actually draw that in. We can draw in something called a dipole. A dipole looks like this. It's drawn from positive to negative. So we draw an arrow from positive to negative like that, and from positive to negative like this. And this indicates the overall view of what's going on with charge separation in the molecule. So we know how to predict whether bonds are polar or not, and it's based on electronegativity difference. But it turns out that molecules can actually be polar or nonpolar, and it depends on both whether the molecule has polar bonds, but also its shape. So the polarity of a molecule depends both on bond polarity as well as shape. And here's why. I've drawn water up there. Let me also draw you the Lewis structure for carbon dioxide. So carbon dioxide, if you remember, has a Lewis structure that looks like this. Carbon in the middle, oxygen here, and here, and I'm just going to draw the most stable resonance structure. And it turns out that oxygen is still a little bit partially negative. So we'll draw that in, orange. Oxygen is partially negative a little bit. This oxygen is also partially negative. The carbon is a little bit partially positive. So there's definitely some polarity going on in these bonds. We could draw their dipoles in like this. We could draw their dipoles in like this. But if you do the Vesper models, you will realize that water is AB2, E2, which means it is bent, and carbon dioxide is AB2, which means it is linear. And so because water is bent, and I've drawn it that way on purpose, the dipoles actually don't cancel out. And you'll notice that there's a net dipole towards the top and towards the middle of that water molecule. And because that net dipole isn't canceled out by anything else, water as a molecule is actually a polar molecule, which gives rise to basically why you're alive today, but that's for another discussion. Carbon dioxide, on the other hand, has dipoles. It has polar bonds, but those polar bonds are pulling, you'll notice here, in opposite directions. So we have the dipole going to the right here, and we have the dipole going to the left here, and they're canceling one another out. So this carbon dioxide molecule is actually non-polar as a molecule, even though it has polar bonds. So there's two types of questions. We might ask you about the polarity of a bond, but we might also ask you about the polarity of a molecule. And what you care about is both bond polarity and the shape of the molecule. So there's kind of a straightforward way to think about this. First off, if you have non-polar bonds throughout the entire molecule, it's non-polar automatically. If the molecule has all non-polar bonds, the molecule is non-polar. But if you have a situation where you have polar bonds and they connect to two different types of atoms, so for instance, let's use HCN, except I can't use H here because the HC bond is nonpolar. So let me just make something up. This is probably ionic, but for the sake of our purposes, we'll deal with it, right? So if I put a sodium there, let's pretend that these are both polar bonds, but it turns out that the polar bond going this way might be a lot greater than the polarity bond going this way. So if you have polar bonds connected to different atoms, you have a situation where you have a polar molecule. So different atoms, then you are going to have a polar molecule as long as the bonds are polar. Or if you have a lone pair or more on the central atom, your molecule is automatically polar. And just so you know, this one takes precedence over nonpolar bonds. So as soon as we see a lone pair on the central atom, our molecule is automatically polar, no questions asked. I don't think we're going to see many cases where we have a lone pair on the central atom and nonpolar bonds. But in order of operations, you care first about the fact that you have lone pairs on the central atom. If that's the case, you're polar in terms of the molecule. If all bonds are nonpolar, you're nonpolar. And then if you have polar bonds, well, if they're all the same, your molecule is nonpolar, like we see here in carbon dioxide. But if they're different, then you have a polar molecule. So let's try this. Let's jump back to our friends on page 10. We're going to identify hybridization as well as the polarity of the molecules. So we're getting a lot going on this page, but we can do it. So hybridization, first off, remember this is based off of our Vesper model. So our Vesper model is AB3E. We have 4 regions of electron density around the central atom. We therefore need 4 orbitals. So our hybridization is sp3. Let's do hybridization for all of these. If we look at CH2Cl2, AB4 has 4 regions of electron density around the central atom. We need 4 orbitals. Will again be sp3. Jumping down to CO2, we only have 2 regions around the central atom of electron density. We only need 2 orbitals. That's sp. If we have AB2 again, then our hybridization is sp because we only have 2 regions requiring electron density. We need 2 orbitals. AB2E is 3 areas of electron density, 2 bonds, 1 lone pair. 3 regions require 3 orbitals, so we'll put 1 s and 2 p's, sp2, and that is going to be the same down here for NO2 because it's also AB2E. It has 3 regions of electron density. We need 3 orbitals, so we have sp2. So there's our hybridization. Let's talk about the polarity of these molecules. Well, right off the bat, we have a lone pair on the central atom. If there's a lone pair on the central atom, automatically, no questions asked, this is a polar molecule. Done. Looking over at CH2Cl2. No lone pairs on the central atom. I can tell you that in this molecule, I know you don't have electronegativity in front of you, but I can tell you that the CH bond is not polar, but the CCl bond is polar. So we can draw in our dipoles. You'll notice I'm putting a little positive end on those arrows. That positive end comes from the positive atom, so dipoles always go positive to negative. Because we have bonds to different atoms, right? So we have polar bonds, we have nonpolar bonds, but we have bonds to different atoms. We are going to say that this is indeed a polar molecule. And that'll actually make a great deal more sense when we can build a model of this molecule and see where those chlorines are located, what a tetrahedral molecule looks like. So if you have questions about the polarity of that molecule, let's build a model in class to make more sense of it. Down here, we have no lone pairs on the central atom. We do have polar bonds. We could draw in the dipoles like so. However, we're bonded to the same atoms, so those polar bonds cancel out. This is a non-polar molecule because you have polar bonds canceling out with one another because there are no lone pairs on the central atom, and those bonds go to the same atoms. Conversely, here again, you have a polar bond. There it is. And it's not canceled out on the other side because we're bonded to different atoms, so this is a polar molecule. Down with ozone, we have a lone pair on the central atom, so right off the bat, automatically we consider this to be polar. And same thing with the nitrite ion, lone pair on the central atom, so automatically this is polar. If there were no lone pairs on those two, because they're bonded to the same terminal atoms, they'd be nonpolar, but the central atom lone pair takes precedence, so those are automatically polar.